So we're looking today at forces, everyday forces, although not always every day, but the effect of these forces with Newton's law. So basically, what's happening when these forces are unbalanced in some slightly different situations, but ones that come up a lot in exams. So they're really useful to know. Let's start off though. Check my pen works. So let's just start off. What is the equation that links force, mass, and acceleration? That should say and. I'll write D in. D and acceleration. What is the equation that links mass to weight? And what is the acceleration due to gravity on Earth? And if you were on the moon, which has a lower acceleration due to gravity, would you have the same weight? So, pause, answer the questions, and I'll go through them in just a second. Done? Splendid. What is the equation that links force, mass, and acceleration? Obviously, the equation is F equals m times a. What's the equation that links mass to weight? Well, weight is equal to mass times g, or m times g. But what is g? G is the acceleration due to gravity on Earth. And what is that value? G is equal to 10. And it's also an acceleration. So that's basically to show you that F equals ma is exactly the same as weight. Weight equals mg, or you could write equals ma, with a being the acceleration due to gravity. Well, if weight equals ma and F equals ma, weight and F, they're the same. So weight is a force. And hopefully you know that. If you were on the moon, which has a lower acceleration due to gravity, would you have the same weight? And the answer is no, because your weight is equal to your mass, which is the same everywhere, times g. And if this g is smaller, and this is the same, this is also smaller. Okay, so we're going to look at a skydiver, everyday forces. Here we go. So forces acting on a skydive. If you jump out of a plane, some things happen to you. What is the main force acting upon you? Actually, there's two main forces acting upon you. One is you being pulled towards the earth, your weight being the main force, the weight, which is the gravitational attraction of the earth, pulling towards you. But as you get faster, what happens? As you get faster, you go through the air and you hit more air particles. And as you get faster, you hit more and more and more air particles. And so your air resistance increases. So at the start, hardly have any air resistance. And then as it goes on, the air resistance increases. And so, let's read this. During the course of a skydive, the weight of a skydiver will not change. As a result of this, the skydiver will have a constant pull downwards, caused by the gravitational attraction of the Earth. Also acting on the skydiver is air resistance, or drag. As the skydiver moves through the air faster, the skydiver will experience more drag. Drag reduces the acceleration the skydiver experiences from 10 meters per second when they've jumped out of the plane to 0 when they reach terminal velocity. We look at that in form of force arrows. So the first thing that happens is when you jump out of the plane, you're not moving for a fraction of a second. And so the only force acting on you is your weight. And your weight is pulling you down. Is that an unbalanced force? Yes, it is. So you start to accelerate down. You get faster, down. But then as you get faster, here, your air resistance starts to increase. Come on, pen. No. There we go. Your air resistance starts to increase. So as your air resistance increase, so we know the resultant force is this arrow up and this arrow down. This arrow is thinner, smaller than the bottom arrow. So therefore, some of this is taken away. So the net force down is less. So you've still got a net force downwards, but it's smaller than it was here. So what's happening is here, the skydiver is accelerating very, very hard, very fast. And here the skydiver is accelerating, come on the pen, the skydiver is accelerating less fast, at a lower rate. After a while, what happens is the air resistance and the weight, come on, no, yeah, the air resistance and the weight balance each other out. They become a balanced force, which means there's no net force, which doesn't mean the skydiver stops falling. That would be insane. It means the skydiver stops getting faster. So here, blue and pen. Here, acceleration. No. Acceleration is quite high. Here, acceleration is reducing, and here acceleration goes to 0. And so at this situation, the skydiver has reached terminal velocity. Now, all of a sudden, the skydiver now needs to pull his parachute. So this bit here is the same. This bit is just terminal velocity, where the skydiver is going as fast as they can because they're not accelerating anymore. And then for a fraction of a second, when the skydiver pulls open the parachute, what happens is the upward force is enormous. It's an insanely huge force. And so what happens is there is a much bigger upward force than there is down. Now, the skydiver doesn't move up. The skydiver just slows down. So what this is saying is for a second, the upward force is much bigger than the downward force. So then the skydiver slows down dramatically. So he was going at 40 miles an hour. But now the upward force is much bigger. So he now starts going, the force is working against, so he starts decelerating. So he slows down to a much nicer speed, much safer speed. And then very soon after that, that upward force and the downward force are balanced because he's going slower. Those forces balance, and then he just they drift down to the earth at a safe speed and land somewhere. If we look at this in terms of a graph, here we have, so section 1. No, this pen is not having it. Okay. So section 1 here. This is when the skydiver jumps. He's got no speed. And then over time, his speed's increasing. And then it gets to a point where his speed increases so much that the air resistance gets so big, it actually stops the speed increasing. So we can see this curve is where his speed is, the acceleration is lowering. It's reducing. He's not getting slower. He's just not getting as fast. And so then here, this is called terminal velocity. This is when the skydiver is not getting any faster. They've reached the speed and they're not getting any faster. That's changed. That's terminal velocity. That's the fastest they can go due to air resistance. Here, point X is when they pull the parachute. For a second, that upward force is so much bigger than the downward force, causing a dramatic drop in velocity, drop in speed. So the speed goes right down. And then, as those air resistance and the speed balance out, we have a new terminal velocity, much lower than the original one. If the skydiver hit the floor at this speed, no. But if the skydiver hits the floor at this speed, it's okay. So if we look at section A, the weight, the downward force, is much greater than the drag. So the skydiver is accelerating. At section B, the weight is equal to the drag. Those two forces, the up and the down, are the same. So therefore, the weight is equal to drag, so we have no change in speed. No change, no force, no change, keeps going at the same speed. Here, the drag is much bigger than the weight. So therefore what happens is there's a net force upwards, causing the skydiver to slow down dramatically. Then, because he slowed down, the air resistance decreases, and here the weight equals the drag again. But because he's going slower and the weight is equal drag, he's not going to go any faster, so he can land nice and safely. Here we have a picture of a rocket. How do we use Newton's third law to describe how a rocket works? You can see that. Now, some people, there's a misconception with rockets. Some people think that hot thrust gas that it's passing pushes down on the floor, pushing the rocket up. But if that's the case, as soon as the rocket's off the floor, that force should drop. And also, it wouldn't work in space. So how does a rocket work? If we apply Newton's third law, if object A exerts a force on object B exerts a force equal and opposite on object A. So what's happening is the rocket is forcing these hot gases down at an incredible speed. The force is here, and the speed of these hot gases is so high and so insane. It's just going at thousands of miles an hour. So as a consequence, excuse me for the sneeze. Sorry about that. As a consequence, no. So the rocket pushes the gases down really fast with a high force, massive force down. So the gases then also have to push the rocket up with an equal and opposite force in the opposite direction. Now, admittedly, the rocket weighs a lot more than the gases. So therefore, the effect of the force on the rocket is nowhere near as much as the effect of the force on the gas. But because the gases are moving so fast with such a massive force, if you apply that same force to the rocket flies up. So basically Newton's law. So the rocket exerts a force on the gases exert an equal and opposite force on the rocket, causing the rocket to lift up. There's a little animation. See? There it is. It looks like it's going relatively slowly there, but you see how fast the gases are going. The rocket's going slower compared to the gases, but still fast enough to take off. You're going to try an experiment today. Interesting. I know. Please don't climb on furniture. I can't supervise you, so don't do anything dangerous. Please don't do anything dangerous. What you're going to need is a stopwatch. Obviously, using your phone is fine. You're at home. A meter ruler. I've got a way around. If you don't have a meter ruler or a tape measure, I have a way around this. And paper. You'll also need some scissors. And what you're going to do is you're going to drop pieces of paper. Now, I've got circles of paper. I have a big circle, a medium circle, and a small circle. I got these by, for the big circle, I just drew around a biscuit tin lid. For the medium circle, I drew around the bottom of the bin. And for the small circle, I drew around the inside of a piece of tape. And what you do is you take your circle and you cut a line in it to the middle. So it's kind of like, hello, a small circle. Okay. Then what you need to do is you need to fold it so it's kind of like an overlap. So we have, looks like this. Can I make this bigger? Oh yeah, check my massive head out. Okay, so here we have circle, wop, wop, wop. Then I'm going to just basically, I'm going to make it into a cone. So I'm going to fold it like this. And so actually what's happened is I've overlapped a quarter. A quarter, shame it's so bright in this room. A quarter of it overlaps, so it's like this. And then use a little bit of tape. A little bit of tape, I've taped it on, and I've made a cone. Do the same with the other one. So, and then you just fold it round, and so like a quarter of it's tucked under. And so I've got another cone, same shape. And a really big one. And then you fold them round like this. So I have three cones: small, medium, small, large. Small, medium, large. There you go. They're all going to sit together like this. Excellent. What we're going to do is you're going to see how long it takes for the object to fall a set distance. So I'm going to suggest you drop it from the inside of a door frame. Door frames are 2 meters high, roughly, unless you have like a massive house. Door frames are about 2 meters high. And what you're going to do is you're going to have your cone like this, and then you're just going to drop it. And time how long it takes to hit the ground. What you're going to do is, so you're going to, let me make my head smaller. You'll vary the size of a falling object and measure the time it takes to fall a certain distance. You'll then calculate the speed of the fall. Write a hypothesis for the experiment. Explain using scientific ideas. So I want you to go, right, I think the small cone will fall faster. I think the big cone will fall faster. I think the medium cone will fall faster. Because, state what you think. Carry out a preliminary experiment. Just check it works. It says we're going to draw a graph. What you're going to do, measure and record your drop height and make sure you can reliably drop the cones from the same height each time. Measure the time taken for the size of the cones to fall. Ideally repeat. And then at the end, you're going to write a conclusion about why the time taken changes. Also, are there any issues? So what I'm going to do is I'm going to have to do a second video with this because I can't edit them together. So I'm just going to suggest, before we go, copy down this table. So copy down this table and then watch the next video where I have a quick go at doing this experiment. Okay?